we go. This is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please don't share personal information during the class for your own security reasons. So we are in the February 6th attendance ticket. I have 9 green checks so far, so everybody who has opened that, make sure I get your green checks. If you're having any trouble opening that, let me know with a red X. Just want to make sure everybody has access to that, no one left behind. Remember, guys, always a good idea that it's always a good idea to write down the password every day, because sometimes things happen to our attendance tickets and they kick us out, and then if you don't have the password you can't get back into it, right? And that's difficult, right? So definitely make sure you write down the password for each day. Just find a document or a journal page or something and just write that down each day. That way you don't miss out on any points, okay? Awesome. So we are on day 7 of the quarter. Do you guys remember how many days are in the quarter? How many school days are in the quarter? I mentioned it once, so if you do remember, I'm going to be really impressed. We do have a quiz today. Yeah, you always have an assignment every day, so it's either a quiz assignment, a game day, a lab, or an exam. No, definitely more than that, Cami. We have, actually, we have 45 days to quarter number 3. So 7, right, doesn't seem like a lot, but 45, it does go by pretty quick. So you're going to definitely see this number shoot up very quickly. Yeah, Tariq Ireland. There you go. All right, so today we're talking about forces and Newton's first law. We do have a quick quiz at the end of class today. It should be super easy. I do want to remind everyone, you do get 5 attempts on every assignment. So don't be upset if you don't do well on something the first time. You can just retake it. You don't have to do anything special to retake it. Just redo it, unless it's an attendance ticket. Remember, you do need the password to retake an attendance ticket, okay? But otherwise, retake things, right? You can do better. I did show you how to find your past attempts, right? You go to progress, quizzes, and then find the assignment, click details, and you can look at all of your past attempts. So that way you can see, what did I get right, what did I get wrong, and that should help you do better on the next attempt. Smiley faces if that makes sense. Smiley faces if that makes sense. Again, you get multiple attempts, never give up, never surrender. Oh wait, no, that's a different thing. All right, so as I was saying though, if you do have a few errors on the 1C lab, I have been getting a lot of emails with corrections. I love it. Make sure you get me those corrections that you need in order to update your grade, and I will definitely get on top of that. Definitely always though give me a little bit of time, just because I'm also working on grading the current stuff, so you'll need to wait until I finish grading that stuff, and then I go back and I grade anything that's old, okay? Remember that we do have an opportunity for extra credit today, so if you come to the 2 p.m. For you all are last names end through Z, so if you come to the 2 p.m. support session today, you can go ahead and get some extra credit as long as you fill out the form that I ask you to fill out. And that's it. It's super fast. Let's see here, and then Star 360 has officially been zeroed out, so if you saw your grade drop a whole bunch, it's probably because you have not done Star 360. Remember, you do need to do both reading and math, so it's worth 50 points, 10% of your grade, but if you only do one or the other, you only get 25 of those points, which is technically an F. So make sure you do both of them. You just need to complete it. You don't need to do great on it, though I do recommend do as well as you can on it, because the better you do, the less live sessions that you have to attend. Okay, awesome. Let me go ahead. I'll give you those instructions again really quickly, just in case you need those. Those instructions are in the content tab, but here's the link to it. Hi Mel, hi Amanda. I'm going to go ahead and send you the attendance ticket for today too. Okay, so that's all that. Today we're going to be... Sorry, I missed a slide. Okay, apparently I have a slide missing. Today, though, we are going to be defining force and describing the different types of forces. We're also going to define inertia and explain Newton's first law of motion. So this entire unit is all about the laws of motion, which kind of define how motion works in our universe. Okay, so we're going to talk all about these different types of forces that you can see up here. There's both non-contact and contact forces, and I'm betting you guys can probably figure out why they're called non-contact and contact forces. But just in case, we're going to still go over it. So remember, we talked about this yesterday, that when we apply a force to a tennis ball, for example, what happens to the tennis ball? When I push the tennis ball, what does it do? Tell me in the chat box. When I push our vampire tennis ball, what does it do? I got an answer from Taylor. I see Andrea typing, Dorian typing. Yeah, it begins to move, right? So it begins to accelerate, get faster, and its velocity changes. Mel, just give it a few moments. Usually it just takes a little bit of time for the screen to load. Okay, so just give it a little bit. If it's still not loading in a little bit, let me know, but it should load eventually. Okay? All right, sorry, as I was saying, forces cause objects to accelerate or change their velocity. So it forces a tennis ball to go from rest to moving, or it forces a car to stop moving. When you apply a brake force, it stops the car, so it goes from moving to stopping. So again, any change in velocity, that is acceleration. Now, these forces can only exist if there are two objects. Okay, and those two objects have to interact with each other. So for example, one object gets pushed and the other object, one object pushes and the other object gets pushed, right? So in this case, the two objects are me and the tennis ball. I'm pushing, the tennis ball is getting pushed. Okay, seems really obvious, but we just need to mention it that you need two things and they need to be interacting with each other in order for there to be a force. And there are going to be two main groups of forces. There's non-contact and contact. What do you think is the difference between them? Tell me in the chat box. What do you think would be the difference between non-contact forces and contact forces? Tell me in the chat box. What do you think? You can also take a look at the board. The answer's on the board, so that should be pretty obvious. Difference between non-contact and contact. Think about, what does the word contact mean? What does the word contact mean? So difference between non-contact, contact. Tell me what you think in the chat box. Looking good. I see Dorian typing. I see Arrow typing. I see Ireland, Israel typing. Looking good. Get your answers in the chat box. What do you think is the difference between non-contact and contact? So non-contact forces are still forces, okay? But yeah, so the word contact means something's touching, right? So non-contact means it's not actually touching. So you can actually have a force that still works between those two objects, even if it's not touching. So for example, when you jump into the air, for a moment you are not touching the earth, but what brings you back down to earth? Tell me in the chat box. What brings you back down to earth when you jump? Yeah, gravity. So gravity is something that works on you even if you're not touching the ground. So gravity is still working on you even if you're not actually touching the other object. Now, contact forces do occur with touching. These are the ones that are a little bit more obvious to us. So for example, literally pushing or pulling something is going to be a contact force, or things like friction. Friction is the force that works against you when you're trying to move something, right? So let's go ahead and talk about those. So here are the three main contact forces that you need to know, besides just pushing and pulling. So the three main contact forces are fluid forces, friction forces, and elastic forces. So fluid forces, you actually experience this anytime you're moving really, really, really fast. Think about it. What happens to your hair when you're driving fast or biking fast or going down a roller coaster or jumping off a cliff or skydiving or bungee jumping? What happens to your hair as you do all of those things? It blows back, right? Your hair begins to be fabulous, blows off into the air. And the reason for that is because the wind, the air, is a fluid, right? It's something that flows and it's pushing against you, okay? So when you're biking really, really fast, this fluid in front of you is actually resisting your motion and it's actually flowing back against you, causing your hair to go all crazy. Okay, so fluids could be anything that flows. This could be water, this could be air, this could be, what else are things? Honey, right? Not that I suggest you go biking in honey, but fluid forces are going to push other objects, okay, even if you don't see them. So air is pushing you even though you don't see it. Thumbs up if that makes sense. Thumbs up if that makes sense. Fluid forces are anything that flows that pushes on you. Excellent. Now, again, this is still a contact force because literally the wind, the air, is in contact with your face, is in contact with your hair, or if you're swimming, the water is in contact with your body. Now, friction forces are our second type of contact force, and these are the forces that resist an object's movement. So, for example, how many of you have ever tried to push a refrigerator across the ground or push something really, really heavy? Tell me, what have you tried to push? Or like a car? I definitely have had to push stalled cars in my lifetime. What is something really heavy that you have had to try to push against the ground or along the ground? Tell me in the chat box. Yeah, a washer, exactly. A car, your chair. Is your chair like a really epic chair? So, yeah, so the reason that these are so hard to push, not just because they're massive, but really it's because the ground is actually working against you. So, surfaces like the ground, because they're not perfectly smooth, if you were to zoom in on the ground, you would actually see mountainous ridges. It would look like a mountain. Because they're not perfectly smooth, they can actually resist the motion of objects. So friction slows you down and keeps you from being able to push those objects. On the other hand, it's also super helpful because without friction, you can't walk uphill. I know many of you might not have ever lived in a cold place, but if you ever have, what happens when you try to walk up an icy hill? What happens when you try to walk up an icy hill that has almost no friction? Yeah, you might make it a few steps, but then you just slide straight back down. Exactly. There's no friction, and so you can't walk uphill. So friction can be a good thing for sure. Now, the last type is elastic forces. So how many of you like to shoot rubber bands at people or have ever been snapped by a rubber band? It's not fun. Yes. Yes. So the reason that these hurt so much is because they have elastic forces. So when you take a rubber band like this and you snap it against somebody, the material, you'll notice, actually returns to its original shape, right? So I'm stretching it, and then I let go, and it returns to how it looked, right? Which really, really hurts, okay? Be nice to your siblings. So materials that return to their original shape when they're stretched or compressed, like a spring, those have elastic forces. But again, you do need to make contact with them, right? This rubber band isn't going to do anything unless I literally stretch it, right? And a spring isn't going to do anything unless I actually push it. Okay, so these are all contact forces. They require physically touching the other object. Okay, let's make sure that that makes sense. Go ahead, grab your whiteboard tools, match these up. These are the three that we just learned about. Hopefully super, super obvious, but let's double check. Want to make sure everyone's on board with us right here. Looking good. Again, you can use any color, but don't use red. And make sure your lines are thin. Thin lines, please, so that it doesn't look crazy messy on the board. That is not a thin line. Thank you. Looking good. It's okay. All right, I'm going to go ahead, pause those tools. It looks like we are on board with all this, so let's go ahead and make sure that these are correct. So I think I agree. Yes, fluid forces, right? They're substances that flow like the air or water that push against you. Friction forces, oh yeah, no worries, Tariq. Friction forces are surfaces that resist an object's motion. And elastic is when materials return to their original shape. Excellent job. Give yourself a round of applause from the smiley face menu. Very well done. Looking good. Now, here are the non-contact forces. So we talked about contact ones. Now, non-contact ones are a little bit harder to think about because, again, they don't actually need to be touching the object. So gravity is the main one. So gravity acts between all objects, and it's based on mass, and it's always attractive. So the bigger the mass, the more gravity it has. That's why the Earth, compared to the moon, which one has more gravity? Which one has more gravity? Think about astronauts jumping on the moon. Which one has more gravity, the Earth or the moon? The Earth, because the Earth is much bigger. Now, that being said, you actually yourself are always attractive, right? So you see my little joke over here, baby, you must be gravity because you're always attractive. This is literally true. You and I have mass, right? We have actual stuff that we're made up of. So since we have mass, we actually do exert gravity on other people, right? So just keep that in mind that regardless of what anyone tells you, you are literally always attractive. Okay, so gravity again acts between all objects, and it's based on mass. Now, that being said, you definitely don't exert as much gravity as the Earth does because you are significantly less massive than the Earth. The Earth has so much gravity because of how big it is. Smiley faces if you understand. Smiley faces if you understand. I learned you're like, oh yeah, I'm attractive. There we go. No matter what anyone tells you, just remember that. Good. Now, electromagnetic forces are the forces between two moving charged particles. So, for example, if you have electrons, all right, electrons, what does that sound like? It sounds like a word that we're pretty familiar. What does electro remind you of? What does electro remind you of? Tell me in the chat box. This prefix. Electro reminds us of what? Yeah, exactly. It reminds you of electricity. So if you think, for example, you charge your phone, hopefully with electricity, right? And so electricity is something that we are very, very familiar with. But what electricity is it's just moving charged particles. It's moving electrons, negatively charged electrons. Now, this idea of moving charges being attracted to each other or repulsed by each other, their forces between them, this is actually what keeps electrons near the nucleus. Take a look here. What charge do electrons have? Those are these green ones. Take a look at those. What charge do electrons have? Yeah, they have a negative charge. What about the protons, the blue protons inside of our nucleus? What charge do blue protons have here? Yeah, they have positives. Now, here's something that you've probably heard many times in your life, but this is also true in physics. Opposites will what? Opposites what? Starts with an A. Opposites attract, right? So this is why electrons stay near the nucleus, because they're oppositely charged. So as they're moving around, the force from the nucleus is keeping the electrons nearby it. Okay, so this is an atom, what everything's made up of, and electrons are being forced to stay nearby because of the force from the nucleus. Okay, now the other thing is that moving particles actually, yeah, basically Ireland with a whole bunch of other people, right? Seems like there's a lot of particles here. So the other thing is that moving charged particles actually create magnetic fields. So depending on how electrons are spinning inside of a material, they can actually create magnetic fields, right? So that's where this idea of magnetic comes from. So electricity and magnetism are actually very related to each other. They just have to do with charges moving. Give me a smiley face if that makes sense. So gravity is mass, based on mass, attractive. Electromagnetic forces based on electricity, charges moving. Awesome. Hi, Andres. Make sure you open up your ticket for today. Just have it open. You don't need to do anything with it yet. Now, the last two are intermolecular forces and the strong nuclear force. And these are kind of like zooming in on really, really small things. So take a look over here. We've got two H's and an O. What are these molecules right here? We've got two H's and an O here. What are these molecules? I'm zoomed in on these molecules. These are molecules of what? They're two hydrogens and an oxygen. Together, that makes what? Yeah, it makes H2O, or water. Now, here's the thing. H2O, how many of you have ever seen like those little bugs in like the nature films that are like walking on water? You guys know what I'm talking about? Yeah. So the thing is, that's what's called water tension. And the reason that water has tension, water tension, is because the water molecules are actually slightly attracted to each other. So these are what are called intermolecular forces, where molecules are actually attracted to each other and they stick together a little bit better than they usually would. So in water, the hydrogens are slightly positively charged and the oxygens are slightly negatively charged. And we literally just said that opposites do what? Opposites what? Tell me again in the chat box. Opposites do what? Opposites attract, right? So those slightly positive hydrogens are literally attracted to the slightly negative oxygens of another water molecule and vice versa. And so the result is those water molecules are a little bit stronger in their relationships with each other than other fluids might be. So this leads to surface tension, to where a bug can actually walk on water for this reason. Okay, pretty crazy to think about. Now, the last one is called the strong nuclear force, and I'm going to tell you this several times throughout the class, but scientists, they're brilliant, but they're not that good at naming things. Or maybe they're really good at naming things, because they literally name things based on what they are, okay? So the strong nuclear force is literally the strongest force in the universe, so they called it the strong force, and it's in the nucleus, okay? So the strong nuclear force, pretty obvious. This is what holds the nucleus of the atom together. So if you take a look at an atom, which is the smallest piece of matter, okay, that we can't see, we have to zoom in a whole lot. But if you take a look at its nucleus, it's made up of neutrons and protons. Okay, now protons are all the same charge. They're all positively charged. So let's think about this. If opposites attract, like charges will do what? If opposites attract, likes will what? Tell me in the chat box. If opposites attract, likes actually do what? Opposites attract, likes. What do you guys think? Tell me in the chat box. What's the opposite of attracting? Yeah, they're not going to attract, right? Opposites are going to do what we call repelling. Okay, so repelling means that they're going to push away from each other. Smiley faces, if that makes sense. That's like when you have two magnets and you try to put the same poles next to each other, they literally push each other apart. So likes repel. So in this case, if you take a look at this, the nucleus is made up of a bunch of like charges. It's made up of a bunch of positive charges. However, the nucleus has this special strong nuclear force from the interaction between neutral neutrons and positive protons that helps to prevent it from repelling. And because of this strong nuclear force, it helps prevent our atoms from destabilizing and destroying all of us. Okay? Because without this, all atoms would fall apart and there would be nothing as we know it. Okay? There'd be a lot of big explosions. Okay? So hopefully we never lose the strong nuclear force. Cool. Okay, let's make sure that these all make sense. Go ahead and match up these terms here. This is also going to be number 1 in your ticket, so make sure, again, you have your ticket ready to go. Grab your whiteboard tools, though. Match these up. What is a force? And then talking about the 4 different non-contact forces that we just talked about. The non-contact forces we just talked about. And Ireland, Tariq. Awesome. I see Dorian on the board. Make sure you're not just copying answers. I can tell you for sure that gravity is incorrect here. There we go. Think about the names of things, right? We've got gravity, electromagnetic, intermolecular, and strong nuclear. Their names, again, for the most part, scientists try to name things super obvious things. All right, gonna go ahead and pause your tools here. Let's shrink these down. All right, looks like we had a little bit of confusion here. So let's go ahead and correct these. Okay, don't copy anything that's up here yet because a lot of these are incorrect. So first off, force, we got this one right. Force is a push or pull. That one's super obvious. Now, gravity, I told you gravity is always attractive. Gravity is always attractive, and it's based on what? Again, think about why does the Earth have more gravity than the moon? What's different about the Earth than the moon? Tell me in the chat box, why does gravity have more why does the Earth have more gravity? It's bigger, it's larger. So that means it's based on mass. So gravity is actually based on mass. Thumbs up if that makes sense. Okay, so we needed to correct that one. Gravity is actually an attractive force based on mass. The bigger you are, the more attractive you are. Excellent. Now, electromagnetic, yes, we got this one. Electromagnetic is the force between moving charged particles, right? Electro, you think electricity, which is just moving charges, okay? Let's go ahead. I'm going to change my color one last time here. Lastly, intermolecular, right? We can literally see the word molecular in this, so that should help us think that it's forces that hold molecules together, right? Molecular molecules being held together. And strong nuclear, you can literally, again, see the word nuclear. So this is what prevents the nucleus from falling apart. Give me a smiley face if all of those make sense. Smiley face if those corrections make sense. This is why we do these checks for understanding, because I know sometimes things can be confusing, especially when we do all of them at once. So hopefully you're learning from your mistakes, learning why you were wrong, and now you can correct it. Awesome. This is number 1 in your ticket. I'm going to go ahead and give you 40 seconds to work on that. Give me a green check when you have number 1 saved in your ticket. Go, go, go. All right, waiting on a few more green checks. So Alicia, Alyssa, Amanda, Amir, Andrea, Andres, Danny, Donnie, Dorian, Dree, Dylan, Edwin, Isaiah. Thank you, Isaiah. Caleb, Matt, Maxine, Michael, Parker, Blossom. Green checks, please, for number 1. Looking good. All right, let's keep on going. All right, so the last thing that we need to talk about today is Newton's first law of motion. And Newton's first law of motion is also called the law of inertia. So let me go ahead. I'm going to read them off for you really quickly. We're going to actually be going over all the laws of motion during this unit, but the one that we're starting with, the first law, is that every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. So those are a lot of words. We're going to go ahead and break it down today. We're going to talk about what does all of that mean. So Newton's first law is also called the law of inertia, which inertia is the resistance of an object to change its state of motion. So inertia is why when you are on the couch eating chips, is it easy to get up and go do something? Tell me in the chat box. If you are on the couch eating some chips, nice and relaxed, is it easy to get up and then go do something? Your mom's like, go clean your room. Nope, it's not. So inertia, right, it keeps us from changing our current state of motion, right? Obviously, that's kind of just a metaphor, but even in reality, if something is not moving, it's going to continue not moving unless something comes and forces it to move, like your mom, okay? Now, on the other hand, if you're already moving, right, if let's say you're going for a run and then something suddenly runs in front of you and you have to stop, is it easy to stop? Tell me in the chat box. If you are running and someone just steps in front of you, is it easy to stop? No. So that's the same issue, that if you are already in motion, it is then very difficult to stop your motion, right? So whichever motion you're in, whether you're at rest, whether you're moving, you're going to want to stay in that state of motion. Okay, so this is inertia, the resistance to change, the resistance to change motion. Okay, now, for example, so what this means is that in outer space, for example, where there is no gravity and no air resistance, right? In outer space, right, there's no gravity, and then air resistance, there's no air in outer space. So both of those things are forces. But without those forces in outer space, an object will just continue moving forever. Okay, so once an object starts moving, it never slows down, it never changes directions, it never stops unless another force acts upon it. This is why it's super important that astronauts, if they're in outer space working on something outside of their rocket ship or whatever, that they stay hooked to the thing, because if they for some reason push off of wherever they are and they're not hooked to it, they will literally keep on moving in that direction forever, and they will never be able to get back to the space station. Smiley faces if that makes sense. Okay, in outer space, once you go in one direction, that's where you're going forever. You will never stop, slow down, or speed up or anything. You're just going in that direction forever. Okay? Yeah, and then they eventually run out of air, and that's not good, right? So, for example, I'm going to go ahead and show this to you really quickly. All right, can everyone see my screen here? No worries. Here is your ticket for today. Cool. All right, so for example, I'm going to go ahead and show the speedometer here. We're going to apply a force to this, so I'm just going to apply a bunch of force, and then I'm going to stop pushing. Okay, just like our astronaut, what is happening with this, with the speed of this object? If there's no outside force, there's no friction, no air resistance, what's happening now that I've pushed this object? Tell me in the chat box. What's happening to its speed now that I have pushed this object? Yeah, so it accelerated, but then what happened to its speed? Take a look at its speed. It's been like this for how, is it slowing down? Look at the red line. Is the red line changing at all? Again, there's no resistance. There's no air resistance, no friction. So yeah, its speed is staying the same. So this is just like outer space. In outer space, if you push something, it will continue at that same speed forever. It will never stop, never slow down, never change directions. Thumbs up if that makes a little bit more sense now. It's never going to stop. Never going to stop in this situation. Awesome. Okay. Now, that being said, sorry, this is number 2 in your ticket. Go ahead, give me a green check when you have it saved. You have 30 seconds. Fill in the blank with the word resistance, just like you see in the red box. Go, go, go. Awesome. Waiting in a few more green checks. Alyssa, Amir, Andres, Tony, Ashton, Bradley, Danny, Donnie, Dorian, Dree, Dylan, Edwin, Isaiah, Matt, Maxine, Blossom, Rozzy, Suji, Taylor. Green checks for number 2 in your attendance ticket. Again, you should have that open. Passwords in the chat box. Looking good. All right, let's keep on going here. So again, let's go ahead. I'm going to give you really quickly your polling tools. If there are no outside forces, what's going to happen to that object? If there are no outside forces, what is going to happen to that object? If there's no friction, no air resistance, we're in outer space, what is going to happen to the object that I've pushed? Awesome, awesome. Getting answers in there. Looking good. No outside forces. There's no friction, no air resistance. We're in outer space. Once I push that object, what happens to it? Correct, correct, correct. Seeing lots of the correct answer. Yes, letter D is correct. It will continue moving forever. It's not going to slow down. It's not going to speed up. It's not going to change directions. If there are no outside forces to work on it, it's just going to keep moving forever. No friction, no air resistance. It keeps moving forever. Okay, excellent job. Now, that being said, what happens if we do introduce actual forces, right? So again, space has no air resistance, has no friction resisting its motion. But that's not true in our reality, right? For example, when you drive, can you just press the pedal once and then lift your foot off and keep driving forever? Is that how it works? That'd be really nice for our gas mileage. But no, instead, you actually have to keep on hitting the accelerator the entire time you're driving, even if your speed never changes. So even if you're going 30 miles per hour the entire time, you still have to be pressing on the gas because friction, air resistance, and if you're going up a hill, gravity are all working against you. Smiley faces if that makes sense. So in real life, things slow us down. In real life, things slow us down. We're not in outer space, right? Okay, so again, space or things like ice are different because there's no friction to slow us down. But in real life, we do have things like friction to slow us down. So let me go ahead and show you really quickly, again, in our demo here. All right, let's go ahead and change this to the friction simulation. Let's give them a little bit of friction. Take a look again at our speedometer. I'm going to start pushing this. Push, 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 push. Get it up to speed. And now look at what's happening to the speed as the box continues moving. What is happening to our red line here, to our speedometer? I pushed it just like the first simulation, but what happened to it? Yes, 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 yes. There we go. Get your answers in the chat box. What happened to the box? I can show you again. Right? Big, 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 big push. But now what's happening? Yes, it's slowing down. So when there's friction, like in real life, it slows it down and prevents it from moving forever. Okay, it won't keep moving forever like in outer space. And this is just like, for example, let me show you here. Okay, if we were in outer space and there was no friction, was no air resistance, then if I dropped this ball, it would just keep on going from one side to the other side forever. From one side to the other side forever. But is that what happens? What just happened to my marble? Again, if I drop it from here, without outside forces, it would keep moving forever. But what's really happening? Yes, it slows down and it eventually stops at the bottom, right? Because friction is preventing it from moving forever. Very, very good. Okay, sorry, I'm going to go ahead and skip this one really quick. So Newton's first law, in essence, says that once something's in motion, it's going to stay in motion with constant velocity, both speed and direction, forever, unless an outside force acts on it. So unless something literally stops it, or unless friction or air resistance are slowing it down. Smiley faces if that makes a little bit more sense. So in an ideal world, like outer space, an object in motion will stay in motion forever. Okay? So it'll have no acceleration, no change in velocity over time. That's what acceleration is, right? Acceleration is velocity over time. So there's no change in velocity over time. It does not stop, does not slow down, does not speed up, does not change direction. Or the other way you can think about it is an object at rest will stay at rest unless an outside force acts upon it. So this is like, for example, if I have a cup and a card here. Okay, sorry, I'm going to actually do it like this. So I have a cup and a card here, okay, and I have a penny on top. So this penny is at rest, right? So this penny is at rest. And the penny wants to stay where? At rest or in motion? If it's at rest right now, what does the penny want to continue doing? Tell me in the chat box. If the penny's at rest, what does it want to continue doing? Yeah, it wants to continue staying at rest. So even once I, for example, flick this card, hold on, let me change my angle. Once I flicked that card, where did the penny go? Did it move with the card? No, it actually stayed at rest to the point where the card was no longer underneath it, and then it had to fall. Okay, so things at rest want to stay at rest, just like you on your couch eating chips, right? All right, this is number 3 in your ticket. Give me a green check when you have it saved. That you have 30 seconds. Fill in the blanks with the word constant and the word change. Go, go, go. All right, waiting on a few more green checks. Alicia, Alyssa, Amanda, Amir, Blossom. All right, everyone. Okay, so that's what we talked about today. We talked about forces and inertia and the first law of motion. I'm going to go ahead and send you your quiz really quickly. Again, all of your answers are in the attendance ticket. So if you have the attendance ticket next to the quiz, you should be able to get 100% on your quiz. Do your quiz with your attendance ticket and then submit them at the same time. All the quiz answers are in the attendance ticket. Okay? Thanks so much, everyone. Hope you have a great day. If you missed anything, it will be in the recording later. Just make sure you save today's password so you can still access the attendance ticket. Otherwise, you are free to log out. Thank you so much, everyone. I will see you later. Bye.